in Greece. He is a musculoskeletal radiologist and a pioneer in the field of radiomics for AI. He is giving us two really interesting talks in the field of AI, and then we will welcome him into the panel discussions and the Q&A afterwards. I would also like to take this opportunity to welcome my co-chair, Dr. Danoub Dalili, for joining us. Thank you.
Thank you very much. Thank you very much for the introduction, but also for the invitation to give these talks. And I would like to congratulate the organizing committee for a very, very successful conference that gives like new ideas and opens new pathways in the area. So in the first talk that I will give to you, I will discuss about radiomics, problems that have arisen in this type of analysis and opportunities that we have to solve these problems and move forward. These are some of my disclosures. So I will start by discussing a bit of the basics of radiomics analysis, challenges in this type of research, steps to overcome these challenges, and what we've done in our lab to standardize the method, and opportunities for future applications. So the whole story with radiomics started with this paper in 2014, where the authors basically described the method to quantitatively evaluate lesions using image analysis. And in essence, this editorial in radiology summarizes what happens there, saying that images are more than pixels, they are data. And since we have data, we have information that we can analyze and build predictive models. I apologize that I'll have to take you back to basic biology to let you understand that radiomics as a term refers to other types of omics, like genomics, for example, that you may have already heard. And in essence, it describes a very detailed way of analyzing very different layers of cellular function, for example, genomics, transcriptomics, proteomics, or whatever else that have to do with the function of a cell. And everything that has to do with the function of a cell relates to the function of a tissue, and this is what we image with our image techniques, and radiomics is basically the analysis of the visual phenotype, the organ phenotype or the tissue phenotype that we see with our imaging methods. So if you see this at a scale, radiomics is at a higher scale, and we have more detailed information in the background that will define what you'll see in the images. So challenges that have to do with radiomics research. First of all, input bias and lack of external testing. I will discuss in more detail about each of the challenges, but this is an overview that I think that these are the most important ones you can find out there. There are other problems as well, but I find this the most important that you'll need to know. Standardization of the method. There are many ways to run a radiomics analysis, and the method needs to be standard, otherwise we'll have reproducibility problems. The very technical nature of the method, not everyone can do such an analysis, and this is usually a problem. And of course, the lack of transparency in reporting radiomics results, the lack of biological correlations. You see some numbers there, you see some radiomics features. You do not understand how these correlate with biological phenotypes. So this is also a problem and reduces the applicability of the method. And of course, the lack of integration of the method with the systems that we use in our hospitals, the PACS systems. So I will start a bit with the input bias and lack of external testing. We have a usual problem that has to do with the selection of the samples for these types of analysis. We usually do studies where we very well defined a nice study population with very strict criteria. But in reality, if you go back to the clinical situation, we don't see the same conditions always, and we have a greater variability. So the method may not be applicable if you test it at a real population. Sometimes you have missing data in your dataset, and that's a problem. Have small datasets. If you try to do an analysis with 30 cases, this may not be generalizable at the end of the day. You may have imbalanced classes, and this means that you have sometimes 10% of your data being tumors, the rest being normal images, and that is a big problem, especially when you evaluate the performance of the algorithm. And of course, in several studies, you have lack of external testing. So, of course, if you have garbage in, you get garbage out, and this destroys the generalizability of the method and the algorithms that you develop. So, the other big problem in radiomics analysis is the standardization of the method. We have multiple ways to extract radiomics features, various scanners and scanning settings, variability among segmentors that has to do with the experience of the person that segments the lesion or variations in drawing the lesion. If I draw the lesion and you draw the same one, you will draw it differently. And of course, operator-induced variability if we have to do with methods like ultrasound, and tissue and modality effect that affects feature stability. Different tissues give different types of radiomics features, and this differs across tissues of different patients. So for all this, we have problems that reduce the reproducibility and the generalizability of the method. So what we've tried to do is, in our lab, we have worked on multi-parameter optimization that is application-driven. And I mean that we've tried, based on the type of images, to do some types of harmonization of the data and also to standardize segmentation algorithms. And of course, we have used methods that are compliant with guidelines like the International Biomarker Standardization Initiative, the Imaging Biomarker Standardization Initiative, the IBSI, and to give you some flavor of what we get with some types of the analysis we do, I'll give you this example with shoulder ultrasound. So we have tried to extract radiomics data from calcifications found on shoulder ultrasound. And we've seen that you can get various images and the quality of the image can vary depending on the settings of the machine or the operator. So we've tried to use several different methods to standardize the images, using the original images as well, but also different image harmonization techniques. And you see that we have analyzed the variability of features, the stability of features with different methods. And on the left, on both images, you see that the stability, the intra-class correlation coefficient of features in the original images is quite low. Whereas if you start doing image harmonization, and especially with techniques like the Clay Advanced that you see here, you see that we significantly increase the intra-class correlation coefficient of the features. So processing of the image before we extract the data makes a significant difference. The other way we've tried to standardize the method is by doing concurrent scanning with modality-specific phantoms. And when I say modality-specific phantoms, we have, in collaboration with our medical physicists, developed phantoms that are specific to ultrasound and CT, and we're now working on an MR phantom, where you, instead of scanning the phantom separately with the patient, you scan the same phantom every time you scan any patient that you have in your department, and you use the same phantom across different scanners. This will basically reduce the variability, help you reduce the variability, because you scan the same thing every time, even if you have different settings or even if you have different patients or different machines. So the phantom goes together with the patient, and you see that we have images where you have the tissues of the patient, and next to the tissues you have the phantom. And this helps us develop what we call normalized radiomics. And what's the point in doing this? You'll see this heat map. You don't need to understand much, but you look at the image and you see that on the left part of the image we have the raw data. On the right part we have the normalized data. With the raw data, you see that you don't see big differences. You don't see groups of colors within the raw data samples. Whereas with the normalized data, you see that we have grouping and different colors identify at least 3 groups within the normalized data category. And you see this on this PCA, where the raw data fall one on top of the other, but when we normalize, we start to uncover things like similarities between high-frequency images or high depth or low frequency. So you uncover information that is not there and is covered by noise when you have the raw data and you don't normalize. And of course, another problem is transparency in radiomics research. I can guarantee to you that in most radiomics papers, you see graphs like this, similar graphs, and the series of graphs is typical for most of radiomics publications. But the question is, so these results that usually give you some positive indication of an algorithm that works very well, that accurately predicts something is usually not reproducible. So you have a result, but you cannot act upon it. So to evaluate the reporting quality of these studies, we have developed with the European Society of Medical Imaging Informatics what we call the metric score, where you can go online and decide, based on the information you find on the paper, the quality of reporting, and you can classify papers from very low quality to excellent quality, and you can also help authors include all the required information and reviewers and editors to assess the quality of the work. And at the end of the day, this increases reproducibility and transparency. The other problem is the technical nature of the method. As you understand, doing such an analysis, segmenting, extracting information, or creating a predictive model requires coding skills, machine learning knowledge, multidimensional data analysis knowledge, model development skills, and at the end of the day, if you don't have this, you either have limited access to this type of research or poor quality research, or the results will stay on paper because they're not of high quality. And I will refer back to my colleague's presentation because this is the reason we have developed the Maestro platform. So we use LLMs to automate this type of analysis, and you can use commands in natural language. You can tell the system that you have images in this folder. It can segment the images for you, extract the required information, filter the data, and at the end of the day, create a model for you and save it for you. So it automates the whole radiomics pipeline. So I would like you to think that radiomics is a way to get signatures from the image signatures from different tissues. So let's say that we have an EMRI, for example, and you can analyze in a very detailed manner different tissues within this image, and you can get the signature, the image signature of the tissues. So we've tried to exploit this type of opportunity that we have here in radiomics analysis to compare images, compare original to synthetic images. And we've used MRIs that have been synthesized by the computer, by AI algorithms, and we have compared the similar ones with the use of radiomics analysis for several different tissues, for fat, for liquid, for bone marrow, muscles. We have extracted data and we have created models that can actually distinguish between the real and the fake images. So you can understand that we have an opportunity there to use radiomics as the stamp, as the signature of high quality image generation. And you see that our models work well, and if you have images that are distinguishable, they can actually tell the difference with a high accuracy. And we have a series of features which construct this radiomics signature. So let's say that you have models like this and predictions that you can do, but you cannot use these models. You are in the radiology department, you want to use them, and you don't have this chance. In this case, you need something that is applicable and your radiologist can actually use. And this is the reason that I call this the ghost model paradigm, because you actually have models that are ghosts. They stay in paper, nobody will ever use them. And that's why we tend to develop applications, online applications or tools like the one I showed already, where you can actually input features and get predictions like this so that you can actually do the whole analysis easily at the radiology department. And of course, if you don't have these systems within a PACS, that's a problem, and that's a big problem with the current version of radiomics models. We'd like to have some kind of PACS integration to bring radiomics to the hands of radiologists. And that's why we have collaborated with a PACS company called Evorat to develop a system that integrates the whole pipeline of radiomics analysis within an online PACS system so that everyone can use and can apply these methods. So at the end of the day, we have to overcome a series of challenges, and the method still needs rigorous standardization to increase reproducibility and generalizability. But we have here image signatures that can be used to assess the quality of our images. And once we establish and make them accessible and easy to use, people will be, at the end of the day, able to use them in clinical practice. I would like to thank my group that works on radiomics and have produced some of these results. So this brings me to the second presentation, which is more applied and has to do with the identification of cases where AI actually fails. The usual case, the usual scenario is this one. You have an AI engineer that has created a model and thinks that the model works very well, but if you put it in a clinical department, it actually massively fails. Even if it massively fails, the metrics are nice, and people think that this is a good model. And that's usually a trap. So we need to find what can go wrong to solve these problems so that we have applicable methods that can be used for the treatment of our patients. Believe me, this is not easy to find. So if you go on PubMed and try to search for failures of AI, you'll find close to 0 papers. And you understand that this is because of publication bias. People usually publish positive results, algorithms that work, and not algorithms that fail. Cases where the algorithms were applied at the hospital and they were a massive success will be published. The ones that never worked usually are never published. So you get a series of positive results, but the negative ones stay in a drawer or are never published. There is this nice study where you see that the negative results of radiomics papers are close to 1% of the results published on radiomics. So to be able to scan papers and search comprehensively into literature about these problems, we compiled a team from the European Society of Medical Imaging Informatics, a big team, that went into a series of papers and tried to identify small parts where they had problems that they were reported even at the supplementary file. And we identified a series of reasons where you can see that AI fails, and these have to do mainly with 3 categories of problems. Problems that have to do with the models themselves, problems that have to do with the infrastructure, and problems that have to do with the human nature of the people that use the actual models. So to give you a flavor of what happens with the models, you need to think of the AI life cycle, and you see that this starts with the inception of the idea of the model and ends up with the deployment, surveillance, and potentially the decommissioning of the algorithm from the hospital if it doesn't work. So at the first step, we need to take into account that all stakeholders, including radiologists, hospitals, patients potentially, need to be involved early so that you increase the acceptability, the usability, the ergonomics of the algorithms. And this will delay later the implementation if you don't take this into account. And of course, you need to have a very clear intended use. People should know exactly what your algorithm does. This is legal responsibility of the company that creates the algorithms. And these are often not declared. This leads to misconceptions, misuse, procurement challenges potentially. And of course, you need to proactively identify risks from the implementation of those algorithms. When you test them, you need to make sure that you have robust results, but in many cases you have limited generalizability. You have algorithmic bias that has to do with representation problems of the population, lack of external testing. And to give you some very important examples, you see that in the UK Biobank, which is an extremely good data set, you have only 6% of non-European ancestry participants. And there has been a study which discussed about the imaging AI data from the US, and you see that between 2015 and 2019, data from the US that was used for AI came mostly from just 3 states, So populations from other places were not actually represented. And that is a problem when you talk about generalizability of the results. Here we come to real-life testing, and usually we have a eureka moment at the stage we have an algorithm that has good performance in the external test set, but new problems may arise when we test this in real life. For example, we may identify anatomical variants which basically confuse our algorithm. We may have new rare or distinct pathologies before developing, before the appearance of COVID. Algorithms would have not seen something that is exactly like this if you had an algorithm for chest X-rays, for example. You may have a typical uptake of contrast media. You may have problems in the administration of the contrast, complex post-op findings, foreign objects, variations in image quality for several reasons, and these could cause problems unless you test in real environments. So testing in real life is extremely important to avoid problems. And imagine that if all these things can reduce the quality of the algorithms, when you have a binary classification problem, benign versus malignant, what happens if you have an algorithm that can detect more than 100 pathologies? And there are algorithms like this, where you have what they call generalist medical AI, where one algorithm can identify up to 100 or more diseases. And the problem propagates and increases and becomes extremely complex. Once you deploy the algorithm and the company comes to your hospital, puts it there, and you start working with it, you may have problems that have to do with post-market surveillance. And there is a regulation related to post-market surveillance from the MDR and the AI Act in the European Union. And actually, this is the formal responsibility of the manufacturers, who must investigate serious incidents. And of course, the providers have the main responsibility. The AI Act involves also the hospitals, the radiologists themselves and radiology departments, who have to provide feedback. They have to collect the data and give back to the company and report any serious incident or unexpected behavior of the model. So we have developed guidance with the European Society of Radiology, which you can find in this paper published last week, where you see that there are things that we need to take into account in terms of post-market surveillance, and a very long list of recommendations of things that companies need to take into account when creating such softwares for radiologists. And of course, if the system doesn't work, or if you don't need it anymore, you don't have more money, or for several reasons you don't want to use it anymore, you have to decommission it. And once you decommission, problems can arise with stored data. Are the data deleted? How long do you store the data? Do you archive them? And if you archive them, who is going to pay for the storage costs? Do you have your own hard drives, or do you have to keep them on cloud, and this incurs a cost as well? And of course, if you decommission the project, the vendor will actually have to access to the patient data. And this is a very nice guide from the NHS which discusses also about product decommissioning and what will happen. When we come briefly to infrastructure, you'll see that we have network issues that may limit the access to the algorithm. The equipment may not be suitable. You may not have integration with PACS, and always you need to take into account the energy efficiency of the models, because you may have huge costs because of energy consumption. And of course, PACS is our friend here, because if you have good integration with PACS and you perform everything using your PACS system, you don't need to export images to external software. You don't need to take 5 extra minutes to do everything. And at the end of the day, you do something easy, you save time and money. With the human factors, I think that this summarizes most of the problems. That psychology of resistance to change, the antidotal effect of organizational justice, support, and leader-member exchange. So basically, it's an exchange between the leaders and the members of the team, inspiring people. And also, we have to think of justice in the access to AI and the perceived organizational support. If you don't have the support, the training, the counseling, and the monitoring of the effect, monitoring of the effect of these measures, you will never want to use them as members of the radiology team of your department. The research reporting problems reduce the reproducibility and the transparency, and of course, if you don't have a transparent application, you have useless AI. And there are checklists that you can use to increase the transparency of reporting in your papers. The main one that you can use for AI in medical imaging is the claim checklist that covers anything that has to do with medical imaging AI, apart from radiomics research. And for this, we have the clear checklist and the metric scores that we already discussed that actually cover peculiarities of radiomics research like feature extraction or feature selection. All the guidelines available can be found on the Equator network, and you actually download the form of the guideline, you complete it, you add missing information to the text, and of course you attach the checklist together with your submission, and you see here that even though that is the correct way to do it, there are several papers that actually say that I completed the checklist or claim that have added information in the text that have never done. So this is important, and editors will check for this information. Of course, you need to share the code of the models, and there are several repositories to share your code with. And of course, we now have methods like the AI passport that can be used to cover all information related to the model so that people can later on use it in a much better way. For performance metrics, you need to select the correct ones for your prevalence of the disease, for the specific use case that you have. You shouldn't rely on accuracy as a single metric. And of course, you should have the clinical context to know which metric to use. We have a list of things that you can use and the guidelines developed by the European Society of Medical Imaging Informatics. Please refer to those guidelines and make sure that you correctly use metrics to represent the performance of your algorithms. So, we saw that we have problems that have to do with models, problems that have to do with infrastructure, and problems that have to do with humans. At the end of the day, bottom line, I think, is that you need to plan early. If you don't plan early and think of the problems in advance, you will have a big difficulty on solving the problems, later on. All these can be found in our paper in the European Journal of Radiology. Thank you very much.
Thank you, Michail. And now it gives me great pleasure to introduce our next speaker. So Dr. Ibrahim Al-Mogi, who